All right, in this video I'm going to talk about inverse relations and inverse functions. So the basic idea is that if you have a function, like this green one right here, then the inverse of the function is simply the reflection of its graph across this line y equals x. Okay, so to get the reflection, we would basically go perpendicular to the line y equals x, and then the distance that we go along this perpendicular is equal to the distance between the graph and the line y equals x. Okay, so this is the distance. So the point on the inverse would be that distance in the other direction along the line y equals x. Okay, so this point right here, if we reflect it across the line y equals x, it's going to go to that point there, and so on. Okay, similar in this case over here, if the green graph is my function, then the blue graph is going to be its inverse, because the blue graph is a reflection of the green one along the line y equals x. Okay, so take this point here, reflect it along the line, across the line y equals x, it's going to go to here. Similar, if I take this point right here, reflect it across, it goes right there, and so on, the sky. Again, when I reflect it across, I'm looking kind of in a perpendicular direction to the line y equals x, and how far on the other side I go is how far away this point is from that line y equals x. Okay, so it's that distance away, so to get the point on the inverse, I go that distance away from the line y equals x. All right, in this case right here, these two functions are not inverses. Because if I look at the reflection, say, of this point here across the line y equals x, it's going to be somewhere over here. Okay, and this point here is not on the graph of the green function, so these two functions are not inverses of one another. Okay, so based on that idea, so here's an important property of inverses. So you know that, so here the green graph and the blue graph, those are inverses of one another. So notice how the point with the x-coordinate 0.1406 and the y-coordinate 0.52 is on the graph of the green function. And if we switch these two coordinates, so then the x-coordinate of a point on the blue graph is 0.52, and the y-coordinate of the point on the blue graph is 0.1406. Okay, so this x-coordinate on the green graph becomes the y-coordinate on the blue graph, and likewise the y-coordinate on the green becomes the x on the blue. So this important property is that if the point AB is on the graph of the function, then the point BA will be on the graph of its inverse. All right, let's look at this question. So here I have a blue graph and a red graph, and they're inverses of one another. So I want to find a point on the blue graph. Well, I know that this point, 0.4, 0.064, is on the red graph. And I know that the blue graph is the inverse. So that means that a point on this graph is going to have an x-coordinate of 0.4. Oops, sorry. The x-coordinate will be the y-coordinate of this point, 0.064. And the x-coordinate of that graph is going to, the y-coordinate of that point is going to be the x-coordinate of this guy. Okay, similarly, so the point negative 0.5, negative 0.125 is on the red graph, so if we reflect across, then we get the point on its inverse, which will be negative 0.125, negative 0.5. Okay, so if the point, A, B is on the graph of a function, then the point B, A, so switch the x and the y, you're going to get a point on the graph of the inverse. So basically, all the x's in the function become the y's in the inverse. Okay, the x's in the function become the y's in the inverse. And so vice versa, the y's in the function become the x's in the inverse. So for that reason, so what's the relationship between the domain and range of a function and those of its inverse? Well, the domain of a function is the range of the inverse. And the range of a function is the domain of the inverse. Okay? So the domain of the function is the range of the inverse, and the range of a function is the domain of the inverse. Okay, so here's a bit of notation. If f of x is a function, then we denote its inverse by this f with a superscript, so that's not a power, with a superscript of a -1 of x. Okay, so here's a specific example. Suppose f of 3 is equal to 5. I want to give the value of f inverse of 5. So we're going to use this idea here. We're going to use the fact that the ordered pair AB is on the graph of the function if and only if the ordered pair BA is on the graph of the inverse. So what's a point? So I know that f of 3 is 5. So what's a point on the graph of f? So the 3 is the x-coordinate, and the 5 is the y-coordinate. So a point on f is 3, 5. This means that 5, 3 is a point on f inverse of x. So what does that mean? It means when the input of f inverse is 5, then the output is 3. Okay? So therefore, f inverse of 5, so again, that's asking for what's the y value for f inverse when the x value is 3. I'm sorry, what's the y value on f inverse when the x value is 5? Well, that y value is 3. Okay? So another way to think about it, okay, so besides writing the point that goes on f and then using that to get the point that goes on f inverse, is we can just interpret what f inverse of 5 is really asking for. So remember that the input of f inverse is an output of f. And so what you're asking for is, this is equal to the value you put into the x in f of x to get 5 as your answer. Okay, so that's what you're really asking when a problem asks you to find f inverse of 5. What's in the parentheses is the output of the original function, and you're looking for the input that goes with it. All right, let's use that idea for this problem. So I know f of x is 3x minus 5, and I want to find the value of f inverse of 2. I'm sorry, f inverse of -2. So -2 here is the output of f. So that means 3x minus 5 equals -2. And the value of f inverse of -2 is what I put in for x, so that the answer is -2. So I add 5 to both sides, and I get 3x equals 3. So that means x is equal to 1. So f inverse of -2 is 1. All right, why don't you press pause while you answer this one. So find f inverse of 4. Okay, so we're going to set f of x equal to this 4. So we have 3x minus 5 equal to 4, and then we solve for x. So we add 5 to both sides. We get 3x equals 9. So that means x will equal 3. So that means the f inverse of 4, so the x value, 3, is what we need to put in here so that the answer is 4. So f inverse of 4 is equal to 3. All right, so I'm not going to do this one, but let's just remember what this is asking for. So f inverse of 1 means, what are we going to put in for x here so that this answer equals 1? All right, and so by inspection, we could see that 6 minus 5 is 1, so that will be 2. to find the equation for f inverse of x, what we do is we say, all right, what was the original one? So y equals 3x minus 5. Well, I know that in the inverse, the x and the y switches. So what I'm going to do is I'm going to switch the x and the y. So I get x equals 3y minus 5, and then I'm going to solve for y. Okay, so again, to find the equation for f inverse, we switch x and y and solve for y. So I get x plus 5 equals 3y, and then I divide by 3. So x plus 5 divided by 3 is equal to y. So that's going to be the equation of my inverse. Okay, and we can actually see that it's consistent with our answers up here. So we said that f of we said that f of negative 2 is 1. So negative 2 plus 5, that's 3. Divided by 3, we get 1. F of 4 is 3. 4 plus 5 is 9. Divided by 3 is 3. Okay, f of 1 is 2. Well, 1 plus 5, f inverse of 1 is 2. 1 plus 5 is 6. Divided by 3 is 2. All right, let's talk about when the inverse of a function is also a function itself. So here I have a case here where I have my function, and I've drawn the inverse here by reflecting across the line y equals x. These are just rough sketches of the inverse. And the question about whether or not the inverse is a function is whether or not the inverse passes the vertical line test. Okay, and we see that that does pass the vertical line test, so this inverse is a function. Over here, this inverse does not pass the vertical line test, so that inverse is not a function. This one doesn't either, so that inverse is not a function. This one does, so the inverse is a function. So in which cases will the inverse not be a function? Well, the inverse is not going to be a function, so let's see why this one here in particular wasn't a function. So if I have this x value of 1, then I have a y value of 1 and a y value of negative 1. Well, where did those come from on the inverse? So here I have 1, 1, and here I have 1, negative 1. Well, this point 1, 1 came from this same spot here because it's on the line y equals x. But where did this point 1, negative 1 come from? It came from over here, negative 1, 1, because the x and the y switched. So because I had two different x's that went with the y value of 1, when I switched it, I got two different y's that go with the x value of 1. Okay? So when I have more than one x that goes with a particular y, then it's going to cause an inverse to not pass the vertical line test. So it won't be a function. So what do I need is the y, so how can we tell ahead of time? Y can't be repeated. Okay, because if y is repeated, then when I take the inverse, x will be repeated. And so that's the rule. When will the inverse be a function? If y is not repeated. Okay, so this brings us to the horizontal line test. So the inverse is a function if and only if each horizontal line intersects the graph of the original in at most one point. Okay, so each horizontal line can intersect the original in at most one point. Then the inverse will be a function. Okay, so here if I look at the original is green one. No horizontal line crosses more than once, so I know the inverse will be a function. Here, I've got a lot of horizontal lines that cross the graph more than once, so the inverse is not a function. Same here. I've got at least one horizontal line that crosses the graph twice, so the inverse will not be a function. Here, again, the green one is the original. No horizontal line crosses the graph more than once, so its inverse will be a function. Okay, let's take a look at this example. So here I have the function f of x equals x squared. well, this is the graph of it. And so this function does not pass the horizontal line test, so I know that its inverse is not a function. But what we like to do in cases like this is we would like to make a restriction on the original graph so that the inverse is a function. And so that's what I'm going to ask to do here. So find a suitable restriction on the domain of f of x so that its inverse is a function.
Hey, oh, I guess I didn't hit press. Sorry.
Okay, then I would like you to find the inverse function. Okay, so in this case what we can do is we can just get rid of the whole left half of the parabola. So we can say that x is greater than or equal to 0. So that's going to be our restriction on the domain. And so then from this we would want to find the inverse function. So what I do is I switch the x and the y. So the original is y equals x squared. So I make it x equals y squared. And I solve for y, and I get y equals plus or minus the square root of x. So I've got to figure out which one it is. And it's going to depend on the restriction we made. So let's just look at the graph of the inverse of this function. So it's going to look like this. And so I see that I have to take the positive square root, because this is not the graph of y equals negative root x. That is the graph of y equals root x. So I know that the inverse of this has to be y equals root x. So f inverse of x will equal square root of x in this case. All right, suppose we took the left half instead. So suppose we got rid of this part and kept the left half. Then our domain restriction in this case would have been x is less than or equal to 0. And so then if we found the inverse function, we're going to switch the x and the y. So x equals y squared. Then we have plus or minus the square root of x equals y. If we do the reflection of this graph right here across the line y equals x, so let's get some of those points. Okay, so this point right here, it's going to look like that. Okay, roughly. We see that this is the graph of y equals negative root x. So if this is our domain restriction, then our inverse is now negative root x.